in our last lesson, we talked about matrix operations. And we talked about addition and subtraction, and then scalar multiplication, which remember was just with a constant. Today we're going to be talking about our matrix multiplication, which means to multiply one matrix by another matrix. So, in order to multiply two matrices, the number of columns in matrix A has to be equal to the number of rows in matrix B. So what that's going to look like is if I have A times B, so remember that we use capital letters to represent a matrix. If my first matrix is an N by M, notice that the number of columns is going to be M for A. So that means that in order to be able to perform this operation, my matrix B would have to have M number of rows. So let's say this was an M by P. So because my inner dimensions, or the columns of my first, the rows of my second are equal, we're allowed to perform this matrix multiplication. And the special thing or cool thing about it is then my resulting matrix is actually going to have dimensions N by P, or the other two dimensions. So let's look at some examples and decide if we can do them or not. So notice it says determine whether each matrix product, which remember is another word for multiplication, is defined. If so, state the dimensions of each product. So on our first one, we have A, which is 3 by 4, and we're wanting to multiply that by B, which is a 4 by 2. So notice that our inner dimensions are both 4. Those are equal. So we can perform this multiplication, and we would end up with something that is the stuff that's left over. So a 3 by 2. Next, going on, I have A, which is a 5 by 3, and I want to multiply that by B, which is a 5 by 4. So notice this time, my inner dimensions are not equal, therefore it is not possible. And we always want to check and make sure that a matrix problem is going to be possible before we do it. So now let's look at actually how we multiply two matrices. We're going to look at the words here for a second. If we're a little bit confused, it's okay. Sometimes it's easier just to see the example. So we'll be looking at an example, or I'll walk you through the actual steps on the next page. So it says the element in the mth row and the rth column of matrix AB is the sum of the products of the corresponding elements in row M of matrix A and column R of matrix B. Something that I'm going to repeat quite often is we are going to go across the first matrix and down the second matrix. So across the first, down the second. I'm going to repeat that a lot just because that's what we're looking for every single time that we multiply. So notice here we have a 2 by 2 times a 2 by 2. So my inner dimensions are the same because they're both 2. So what we're going to do is we're going to look at row 1 of matrix A. So I'm going across my first and down my second. And basically I multiply the corresponding parts. So I have A times E. Then I'm going to put a addition sign in between, and then I have B times G. And then basically we move on to the next column. We're still using the same row though in matrix A. So we're still using AB, but this time we're using FH. So again, across our first, so A times F, across B, down H, so we end up with AF plus BH. And because I'm using the first row, second column, that's going to go in the first row, second column entry of my resulting matrix. And then we would continue that. If I had more rows to use in matrix B, I would just keep going until we're finished. In this case, that's my only, or that's my last column, so that's where we would stop. And then basically we're going to start the process over again, but with our second row in column A. So this time I'm using CD. So I'm using the second row. So these are going to be my second row entries of my resulting. And then I'm going to multiply it first by the first column in B. So we would do C times E plus D times G. Again, moving on, we're using that same row in A, but we're going to move on to our second column. So we would have C times F plus D times H. So I know that's a lot of letters. So let's look at an actual example with numbers. And I think that might at least help it a little bit. So we have x times y, and they give us a 2 by 2 times a 2 by 2. And that's important because remember, we need to check and make sure that our inner dimensions are the same. They are both 2, so we are allowed to do it. So I'm going to go ahead and write that out. So I have 6, negative 10, negative 3, negative 2, and we're multiplying by negative 5, 3, negative 4, 3. Now I'm going to write out every single step in this case just so we can see where all of our numbers are coming from. And I do want you to write out your steps when you do your homework. However, you don't have to write out like as many of the steps that I write out. If you want to skip and simplify a little bit, that's fine. But I am going to write out all of them for right now. That way we can kind of see where all of the numbers are coming from. So we want to start same way we did before in our definition with our first row in our first matrix. And then we're going to start with the first column in our second matrix. So I'm looking at 6. So I need to do 6 times negative 5. And then our kind of catchphrase, like we said, we're going across our first, down our second. So then I'm going to add negative 3 times 3. Moving on, we need to do that same process, but now with our second column in our second matrix. So again, we're going to do 6 times, this time we're using the negative 4. We're adding, going across our first to the negative 3 again, down our second to the 3. Okay, and we'll simplify that here in a second, but like I said, I want us to see where all the numbers are coming from. And again, we would continue that process if we had any more columns, which we don't, so that's going to be it for right now. Then moving on to our second row, we're looking at negative 10, 2, and negative 2, sorry, and we're repeating that process. So my second row, first column, is going to go in my second row, first column entry of my new matrix. So I'm going to have negative 10 times negative 5 plus negative 2 times 3. Again, going on, we're using that same row, but our second column this time. So we have negative 10 times negative 4 plus negative 2 times 3. And this is going to be my resulting matrix. And then we're just going to simplify everything. So notice that 6 times a negative 5 is going to give me negative 30. Then I'm going to add a negative 9 going across. 6 times a negative 4 is going to give me a negative 24. And we're adding a negative 9. Then here I have negative 10 times negative 5, which is going to give me a positive 50. And then I'm going to add a negative 9. On our second row, second column, we have negative, it's going to be positive because we have a negative times a negative. So positive 40 plus a negative 6. So then just simplifying those one step further, I get negative 39, negative 33, positive 41, and a positive 34. And that would be my resulting matrix. And notice that it's going to be a 2 by 2 because those were the outer dimensions of the two matrices that I was multiplying by. So let's look at another example. It says find the product of each. I have G times H. So looking at our G, I want to write it first. I have 1, 3, negative 5, 4, negative 2, 0. And we want to multiply that by 2, 3, negative 2, negative 8, 1, 7. Again, needing to check our inner dimensions. Notice that G is a 2 by 3, and H is a 3 by 2. So those inner dimensions are the same, so we are okay to go ahead with our multiplication. And hopefully we can see that we're going to end up with a 2 by 2. So again, starting that process, I'm using the first row of my first matrix and my first column of my second matrix. So I'm going to have 1 times 2 plus 3 times negative 2. And again, we're going to continue on. This time we have 3 elements in each of those, but we just continue on with that addition. So we have plus negative 5 times 1. And again, we'll simplify here in a moment, but I want us to see where I'm getting all of these from. So we used our first row, first column, so then we're going to go on and use our first row, second column with that same process. So this time I have 1 times 3 plus 3 times a negative 8 plus negative 5 times 7. I don't have any more columns, so I'm done with my first row. Again, moving on, we're going to move to our second row and start that process over again. So I have 4 times 2, so I'm starting with my first column again, plus negative 2 times negative 2, and then plus 0 times 1. Moving on to our second column, and still using that second row, we have 4 times 3 plus negative 2 times negative 8 plus 0 times 7. So simplifying, we get 2 minus 6 minus 5, 3, and then we have a 3 times a negative 8, which is going to give us a negative 24. And then negative 5 times 7 is going to give us a negative 35. Going on to our second row, we have 8 A negative times a negative gives us a positive, so plus 4 plus 0. And then we have 12 plus 16 plus 0. So then simplifying for our last step, we end up with negative 9, 12, negative 56, and 28. And so that would be my resulting matrix. And notice that we did get a 2 by 2 like we thought we would. So now, let's look at our next example. Oops, let's clear that off. So this time I'm wanting to do H times G. So notice that on our first one, we did G times H. This time we're wanting to do H times G. And again, we do need to check our dimensions. So notice that H is a 3 by 2. Okay, and G is a 2 by 3. So those inner dimensions are the same. So we're okay to go ahead and do our multiplication. And notice though, this time we should end up with a 3 by 3. So getting my problem set up. So this time we have H times G. All right, so again, we want to look at that first row, so 2, 3, and our first column. So I'm going to do 2 times 1, so first entry. Remember, we're going to go across our first, so plus 3, down our second, so times 4. And we only have 2 entries this time in each row and column, so we only have to add 2 things. So then going on to our second column, but still using that first row, we have 2 times 3 plus 3 times a negative 2. And then lastly, our last column, we have 2 times negative 5 plus 3 times 0. Going on to our second row of our first one now, we have negative 2 times 1 plus negative 8 times 4. Going on to our second column, I have negative 2 times 3 plus negative 8 times negative 2. And then lastly, we have negative 2 times negative 5 plus negative 8 times 0. Moving on to our last row in our first one, we have 1 times 1 plus 7 times 4, 1 times 3 plus 7 times negative 2, and then 1 times negative 5 plus 7 times 0. Now, reducing all of those, we get 2 plus 12. 6 minus 6, negative 10 plus 0, negative 2 minus 32, negative 6 plus a positive 16, positive 10 plus 0, 1 plus 28, 3 minus 14, and negative 5 plus 0. So my last step, simplify that one more time. I get 2 plus 12 gives me 14. 6 minus 6 gives me 0, negative 10. Negative 2 minus 32 gives me a negative 34. Negative 6 plus 16 gives me 10. Positive 10 plus 0 gives me 10. 1 plus 28 gives me 29. 3 minus 14 gives me negative 11. And then negative 5. And so that would be my final answer. Now, something important to point out, notice here, we got a 3 by 3. We used the same two matrices that we used in our first example, but we switched the order, and we got a different matrix. They're not even the same size. And that's an important property, or lack of property. Because remember, with our normal multiplication, 2 times 3 is 6. 3 times 2 is 6. Remember that that's called our commutative property. But in matrix multiplication, we have no commutative property. Or in other words, the order that we do stuff matters. We do have a few other properties though that do work. One of them is the associative properties. Remember, that's just regrouping things in a different way. So we could do A times B first, then multiply by C. Or we could do B times C first, and then multiply by A. If we're multiplying by a scalar, we also have an associative property. So we can multiply our two matrices together first, then multiply by that scalar. Or we can multiply the scalar to either one of our matrices first, and then multiply by the second matrix. And then we actually have two distributive properties. The reason for that is because we have no commutative property. That means that we have to make sure that if my other matrix is on the left-hand side, I have to apply that or distribute it to the left-hand side of both of my inside matrices. If my other matrix is on the right-hand side, I can still distribute it, but now we have to distribute it to the right-hand side of both of our matrices. So we can use those properties, but just be careful because remember that the order matters for all of these.